In this video, we'll look at trigonometry of right triangles. So previously, we've defined the trigonometric ratios in terms of real numbers. That is, we thought of it in terms of the unit circle, starting at the coordinate pair 1, 0, tracing along the edge of the unit circle, ending at a terminal point P with coordinates x and y, and with those, we defined our trigonometric ratios. Now we're going to kind of switch gears a little bit, and we're going to talk about the trigonometry of acute angles, that is, the trigonometry of triangles, specifically right triangles. So first we'll go through all the trigonometric ratios. We'll talk through briefly how to calculate the trigonometric ratios on calculators, and then we'll talk through our special right triangles. So like I was just saying, recall the definition of the trig functions as defined on the unit circle. So we would start here at the point 1, 0, trace along some real amount along the edge of the unit circle, and end at terminal point P with coordinates x, y. With those coordinates, we were able to define the trigonometric ratios. So now we're going to look at an acute angle, theta, here. Notice that this angle over here would also be acute. For this acute angle theta, we have to give words to the different sides so we can talk about what side is in ratio with what side. So of course with the right triangle we have a hypotenuse, and we'll typically abbreviate that as H, hypotenuse. That's the side opposite of the right angle. Then for the side opposite our theta, we call that the opposite side, abbreviating it as O. And then the side right next to it that is not the hypotenuse, we call the adjacent side, abbreviating that as A. So we've got a side opposite of theta, adjacent to theta, and the hypotenuse of our right triangle. With these, we can define the trig ratios for acute angles in right triangles. So the trigonometric ratios. I've given you 3 other examples of right triangles so you can see that the opposite and adjacent sides of the right triangle are defined relative to the theta. So, in this theta, we've got the opposite side and the adjacent side. With this theta, we have an opposite and an adjacent side. And lastly, with this theta, this is the opposite and this is the adjacent side. For sine theta, we have the opposite side over the hypotenuse. For cosine theta, we have the adjacent side over the hypotenuse. For tangent, we have the opposite side over the adjacent side. Cosecant, hypotenuse over opposite side. Secant theta, we have the hypotenuse over the adjacent side. And cotangent of theta, we have the adjacent side over the opposite side. A good mnemonic to remember this is SOHCAHTOA. You've maybe heard of this one before, but we read this as sine is defined as the opposite side over the hypotenuse. Cosine is defined as the adjacent side over the hypotenuse. And tangent is defined as the opposite side over the adjacent side. So SOHCAHTOA is a nice mnemonic. And then to remember the second row, cosecant, secant, and cotangent, just remember that those are all the reciprocals of the top row. So calculating the trigonometric ratios sine, cosine, and tangent are all easy to do on a calculator. Those 3 functions are typically built into the functionality of a calculator. However, cosecant, secant, and cotangent are not usually built in, they're not usually functions built into a calculator. So it's important to remember that cosecant is the reciprocal of sine, and we can write that as 1 over sine theta. Secant we can write as 1 over cosine theta, and cotangent we can write as 1 over tangent theta. This is really important because, like I said, you won't always have cosecant, secant, or cotangent on your calculator, so just remember that you have these reciprocal identities to help you out in those cases. So now we'll look at the special right triangles, and I'll do a couple evaluations of these trigonometric ratios using our right triangles. So consider the two figures below. On the left, we have a square, a perfect square, with side length 1. So we've got one here and we have one here. And since we have one on those two sides by the Pythagorean theorem, we've got the square root of 2 as the diagonal. Now, since the diagonal bisects the angles here and here, we can say that the angles inside are 45 degrees and 45 degrees. So we have what we'll call a 45, 45, 90 triangle, indicating the degrees, the angle of the three angles inside that triangle. In the figure on the right, triangle ABC, we have an equilateral triangle of side length 2, and if we drop a line from B to bisect AC, we'll have two lengths, 1 and 1. So we have a side length 2 and a side length 1. And at our right angle, since that's opposite of 2, we know that 2 squared must equal 1 squared plus this side squared, which we then calculate to be the square root of 3. Since all the angles inside an equilateral triangle are 60 degrees, we can say that we have an angle of 60 degrees, an angle bisected, so 30 degrees, and a 90 degree angle. So we'll call this a 30, 60, 90 triangle. And these are really useful because these numbers tend to come up rather frequently. Now, as an example of evaluating a trigonometric function at a particular angle, let's look at this angle here, this 45 degree angle. So now let's calculate the sine of 45 degrees. So first we need the length opposite, the length of the side opposite this 45 degree angle measure, and that's 1. And then we need the length of the hypotenuse, which is square root of 2. And if we rationalize it, we know that this becomes the square root of 2 over 2. Now don't forget your mnemonic, SOHCAHTOA, in case you forget. Now for the next one, let's do the tangent of 60 degrees, this angle here. So we're going to find tangent of 60 degrees. And tangent is defined as the opposite side over the adjacent side. So we get the square root of 3 over 1, which is the square root of 3. I'm not going to do all of these special values of trigonometric functions. Instead, we will move to the next page. The special values of the trigonometric functions. The following values of trigonometric functions are obtained from the special right triangles. So I've drawn two triangles, one a 45, 45, 90, and one a 30, 60, 90 triangle. And then our first column here, I have theta in degrees, then theta in radians, and the value of each one of our trigonometric functions at these special angles.